For the Snell's Law, it is the relationship of the sine of an angle, incident angle. So when the light comes in, so when the light is coming in, it has an incident angle, and when it gets into a different medium, it has refraction angle. So refraction angle and incident angle. So the index of refraction is the relationship of the light in the vacuum over the speed of the light of the vacuum in speed of the light in different medium. So index of refraction has n, and it is the relationship of the speed of the light in the vacuum, or air is almost the same, and over the speed of the light in the different medium. This is very important to remember. Then when waves go from one medium to another, they don't change their frequency because the frequency depends on the source of the waves, so frequency stays the same. So if you look at this formula, n is equal to the speed of the light over the velocity in the medium, and the velocity of the wave is equal to lambda times the frequency, and again lambda times the frequency. And this is the this lambda is in the vacuum. This is why there's a little zero right there. There's a zero in the formula, and divided by wavelength in the medium, but the frequency stays the same. So you could rewrite as index of refraction equals to the speed of the wave in vacuum over the speed in medium, or the wavelength in the vacuum over the wavelength in the medium. Because when the wave is going from one medium to another, frequency stays the same, speed changes, and the wavelength changes. So the velocity of the wave is equal to lambda times the frequency. So if the frequency stays the same and the velocity increased, so the wavelength is going to increase. And if the velocity decreased, so the wavelength is going to decrease. And for Snell's law, it has a relationship of, so index of refraction in the vacuum, let's say index of refraction, I'm going to call this N1. So in our case, if the air has index of refraction N1, and index, the angle of incidence is theta 1, and in the angle of refraction is theta 2, and the water, or this is glass, right? The glass is N2. Then the Snell's law states that N1 sine theta 1 is equal to N2 sine theta 2. So this would be the equation for the Snell's law. But we know that N1 would be C over V1, which is velocity of the medium in the air, and N2 is equal to C over V2, which is the velocity in the water, or glass, in our case glass. Then I can rewrite N1 as C over V1 sine theta 1 is equal to C over V2 sine theta 2. And if C and C cancels, the speed of light cancels, then I have this formula that is given in the lesson, and that I'm putting the box around. So that gives you this formula. So Snell's law originally states relationship between the incident angle and the indexes of refraction and the angle of refraction, right? It states it like the way it's written, but it also can be rewritten different ways. So it also could be rewritten this way, and it is easy to derive. So if I have sine theta 1 over V1 is equal to sine theta 2 over V2, I could rewrite it as, if I look at this way, let me show an example. So 4/16 is the same as 6/24. But I could also rewrite it this way. 4/6 is the same as 16/24 and equals to 2/3. So I can rewrite my fractions horizontally, like looking horizontally. So I could write sine theta 1 over sine theta 2 is equal to V1 over V2. So this is how you get this formula that is given in your lesson. Here's an example of flat refracting surfaces, and I'm going to derive the formula for you, like the formula that you see right here, because we're going to be using this formula right now for solving a problem. They usually show similar questions on AP exam. So what we have here is there is an object underneath the water, and when your eye, so let's say the light reflects off an object, and when it gets into the medium that is not so dense, the angle of refraction in this case is larger than the incident angle. But when the object is observed by an eye, it actually observed at this height. So the eye does not know that the angle changes, and the eye would just see, oh, the object is right here. And then again, another ray would come up from the object that is underneath the water, and then would refract again from the normal. And if you continue that angle, that ray, that again, the object is appearing much higher than it is actually positioned. So I'm gonna call this part, oh, they already have it. This part is HO, and this one is HI for the incident angle. So if I look at this part right here, this line and this line are parallel, so this angle and this is the same. I'm gonna call this part X. So I'm gonna say that tangent theta, and this is theta O, and this is gonna be theta I, because it's incident and refracted. So I'm gonna say that tangent of theta O, so this is theta sub O and this is theta sub O, is equal to, so I'm gonna erase this so you can see this is theta sub O. So have it like this. This is theta sub O and this is theta sub O, and this is X, is equal to the opposite over adjacent, so that gives me X over HI, and theta tangent of theta I is equal to X over, so again this is going to be your X, and this will be your H sub O, so that's going to be X over H sub O. And because the difference between these two angles is so little, we say that the tangent of small angles are equal to the sine of the small angles, and you can try this in your calculator. So this would be the sine of theta incident. So for the small angles, your sine is equal to tangent. So you can do sine of 1, sine of 2, sine of 3, and check that the numbers are going to be very close. And then I'm going to write another formula, Snell's Law. I'm going to say N1, which is air, or let's call it N sub 0, sine theta sub 0, so this is our sub 0, and this is incident, is equal to an incident because it is incident because it's coming from the water into the air. So this is your incident angle, this is your incident, and that is refracted, is sine incident, right? So I can say that, let me do it this way. If I look at this part, I can write this is equal to that over that. So I can say x over h incident divided by x over h o is equal to sine theta I over sine theta o. And for this part, I have x over hi is equal to x over ho divide. I'm gonna flip it, and that will give me ho over hi. So that's ho over hi. And here I can also say that sine I over sine o is equal to, so I have sine I over sine o. So I'm going to divide both sides by sine o, and I'm going to divide both sides by ni. So that gives me no over ni. And I got the same formula that they give you over here. So they just write it this way. They wrote it like this. They wrote NO, actually this way, over HO is equal to, that's N, NI over HI. And the negative sign, you don't have to worry about it right now. When we do optics, you will understand that part, but for now, just this. So here's an example question. A scuba diver training in a pool looks at his instructor as shown in the figure. What angle does the ray from the instructor's face make with the perpendicular to the water at the point where the ray enters? The angle between the ray in the water and the perpendicular to the water is 25 degrees. So the angle that they ask you is this one. They ask you, what angle does the ray from the instructor's face make with the perpendicular of the water at the point where the ray enters? So this is the normal, and the ray enters at that point. So I'm going to look at this triangle. And I'm going to look at this triangle. And this is your incident angle. And this is going to be our refracted angle. This is your N1. Well, let's do an incident and refracted. And they give you the depth. So the depth is given. And they give you the how far the instructor is from where the ray enters. So I can say that using Snell's law, N incident sine theta incident is equal to N refracted and sine theta refracted. And I don't give it to you here in the problem, but N of the air, so index, is equal to 1, and N of the water or refracted medium is 133. So now if I plug in my numbers, I have 1 sine of theta, I'm looking for this angle, is equal to 133, and this angle is given 25. So I can find what sine of theta I is equal to, which is 133 times sine 25. And that gives me theta I is equal to arc sine of 133 sine of 25. And that is 34.2 degrees. So this is this angle. And I guess the question when they ask you is, what the angle does the ray from the instructors make with the perpendicular to the water? I guess they ask you this angle, so that would be 90 minus 34.2, and that gives you this angle. Here's another example. In the figure provided, assume that the incident beam strikes the prism with an angle of incidence, and they give you angle of incidence 60 degrees. So that means if there was a perpendicular, this would be your angle of incidence, and this would be your angle of refraction. If the top angle of the prism has measure of 60 degrees, what is the angle of refraction of the red light and violet light when the beam enters from the emerges from the other side? So we want to find out the angle. So I need to make a perpendicular here, and I want to know this angle when it emerges from the other side. What is that angle? So let's call this theta 1, theta 2. I'm going to call this theta 3 and theta 4. And they give you that index of refraction for the red light is 1502. So I'm going to do red light, and then you can try to do yourself for the violet light. So index of refraction is equal to, for the red light, 1502. And the angle is given 60 degrees. So I'm going to use Snell's Law, and this is, I'm going to call this sub-zero. So I have n sub-zero sine 60 is equal to n, the one that they give you 1502, sine theta 2. So this is 1, index of refraction for air is 1, sine 60 is equal to 1502 sine of theta 2. So that gives me theta 2 is equal to 35.2 degrees. And then let's look in this triangle. So if I have this one perpendicular and that one perpendicular, and I have a ray that is coming, I don't know, I'm just gonna do it like this. So if this one is 35.2 degrees, and they say that the angle of the prism has a measure of 60 degrees, so that is also 60 degrees. Then if this is 35.2 and this whole thing is 90 degrees, so the other side is also 90 degrees, then the angle right here is 54.8. This one is 60. And in this triangle right here, the sum of all the angles should be equal to 180. So I'm going to subtract from 180 60, and 54.8 gives me 65.2. So this part is 65.2 degrees. So now, because this again 90 degrees, I can find out what this angle is, which is the incident for the other side of the prism. So that is 90 minus 65.8. 65.2 and gives me 24.8. So this angle is, that angle is 24.8 degrees. So now I can do again Snell's Law. So this is degrees. So for the second part, I will say the angle of incidence. So this angle of incidence, let me do a different color. Let's keep it red. So the angle of incidence, this one is 24.8, but when it comes out, there is another angle, theta 4, and that's the one that we're looking for. So I'm gonna use again n in this refraction, and sine of 24.8 is equal to n of the air, so I'm going to do sub-zero, and sine of theta 4. Then I'm going to plug in, this is 1, then I have sine 24.8 is equal to, oh no, n is not 1, n is 1502, right? Because that was the n of the prism for the red light. And then outside is 1, and then I have sine theta 4. So theta 4 is equal to arc sine of this whole thing, 1502 sine 24.8. So theta 4 is equal to 39.05 degrees. And here I have all the things broken down for you, and you can work out the same for the violet and check that you getting the same answers.